Yeah, it's okay now, right? The guy who is come back. Ah, here. Okay. So we just again just summarize what I did in the morning a little bit, and then we proceed. Okay. So what I did is that I was talking about a Hamiltonian, right? I mean, this is Ising model, and we wrote SI plus 1, and also we put a field summation over I SI plus 1 and summation of SI. Okay. So this we write S by 2 SI plus 1. So just to symmetrize. Okay. And then we for both H equal to 0, not equal to 0, transform matrices we know. And for any system, what we discuss is that we generally talk of systems where you do not know Hamiltonians, like Hamiltonian can be anything, so you do not know what. And then if you have a variable, it is given by this variable ni at each lattice site. This is one dimensional systems. At each point you have a site ni, and ni can take values, let us say 1, 2 up to q. These are the site variables. So now what you discuss is that E, this is also equivalent to E. So what we know is that P of probability of a configuration is e to the power minus beta E of C divided by Z, and Z is just trace of T to the power L. So this is just trace of T to the power L, and what we write here, E is basically the configuration is something like 1, 2 or whatever you write, 3 maybe 2, 1, 1, 3, 3, 1, I mean putting q equal to 3. So it's a sequence of 1, 2 or 3, and what we say is that for each, right, I mean at each site you replace the site variable by a corresponding matrix. Okay. So what I replace is that you replace by d by d1, 2 by d2, 3 by d3 and d2, like that. So you get a matrix. Okay. So what you want to write is that e to the power minus beta E, you just write as if this is trace of this matrix tree. So d1, d2, d3, d2, like that. Okay. So the general answer is that probability of a configuration is that you replace the configuration, the units of the configuration, whatever the each site, you replace by corresponding matrix, that becomes a matrix product, make a trace and divide by T to the power L. Okay. So this is what we find generally true for any Hamiltonian in whatever it is. Okay. So what will be this matrices D depends on what is the Hamiltonian, right? And D and D1, D2, all these matrices. Okay. And we have, right, I mean there are, if it is Q types, so there are Q different types of Ds. Okay. For each one corresponding to one site variable, and this is the first equation. So P of C. So I just, this is the equation which we want. Okay. And then what we have also calculated is that dk, any k, so this is just transfer matrix T times kk. Okay. Or if you call nk, whichever we call, right? I mean not kk, nk, nk. Huh. What is the factor? Here. Yeah. It is okay, it is the same thing. Because this sum, whatever it gives, this sum on the ring, it will give the same thing. 2 cancels out.
What cancels?
Summation over SI is same as summation over SI plus 1, right? Because summation over SI basically sum of all whatever we write in different sites, right? Sum of SI plus 1 is also the same. Yes, summation, that is, yeah, true. Okay, for her it is better. Okay, it's okay. The same thing. You did not get a point that it was. Okay, okay, great. So P of C is just trace of this divided by trace of T to the power L. Okay. So now what we do is that D1, for example, D1, this equal to T times 1, 1. Okay. Okay. So that is right. I mean that's what we wrote earlier. So dk equal to T K K. Okay. So for example, if it is an Ising model, so for Ising model, this D1 and D2 I can represent is D plus and D minus. Okay. D minus I was representing by E, and D plus I was representing by D. Okay. And then I find that D equal to T times plus plus, and E equal to T times minus minus, and T equal to D plus E. Okay. So the general notation, right? I mean, this is just T to the power, right? I mean, for maybe let me see. So basically, this is just trace of T to the power L is written. So basically, trace of T to the power L was written. So you can write T times I, and I can be broken into plus plus minus minus, like 1 1 plus 2 2 plus 3 3 in whatever dimension you have. Okay. So each of them can represent a particular species, right? I mean, T times I, this equal to T times 1 1 plus 2 2, like that. And T equal to, so basically just all I want to write is T equal to summation over K T K K. Okay. So basically this sum is only on this is identity. Okay. So each of the term you can represent is dk. So this is equal to summation over K dk. Okay. So dk equal to Tkk, that you can identify very simply. And for Ising model, this is this. So we have found out what is the representation. So this is T is e to the power beta, e to the power minus beta. If you multiply, this is just matrix 1 0 0 0, and then if you multiply, this is you just get e to the power beta, e to the power minus beta 0 0. That's your D, and this one is 0 0, e to the power minus beta, e to the power beta. Okay. So that's your matrices. Okay. So these are D and E. This is what we found. Okay. And then we try to find out. So these are the general one for any dk equal to that. So I keep this notation, and T equal to summation over K dk. Okay. And then partition function, of course, Z equal to trace of T to the power L. Okay. And then after this, what we are trying to find is that trace of T to the power L. So this one in large L limit, L going to infinity limit, this one is just lambda max to the power L. Okay. So the partition function depends only on lambda max to the power L. So whatever can be derived from partition function, like in start make, like you can differentiate the partition function or log of the partition function few times here and there, and you can find whatever quantities. Okay, whatever quantities can be obtained by differentiating only partition function, they only relate to the largest eigenvalue of the transfer matrix. That's all. Okay. So and log of Z is of log of lambda max to the power L, which is L times log of lambda max. So this is proportional to the volume. Okay. So this is a quantity which you call the free energy. It's like energy. Like if you increase double the system size, the energy will be doubled. It's like free energy. So this is the free energy. Log of Z is just free energy, and then this is just a difference. So basically, lambda max, the analytical continuity of lambda max tells you whether there is a phase transition or not. And we say, how it is. I'm not drawing that picture again. That we say that eigenvalue crossing, right? Different eigenvalues if you plot, if the largest eigenvalue is crossed by some other one, then you have lambda max actually changing the behavior, and there you have a phase transition. And the type of phase transition depends on how they cross. That's what we discussed. Okay. And then on the top of it, we also say that so the
also allowed to look at the temperature, right? Because lambda max will be a function of
temperature. Yeah, it can.
So
Yeah.
TC can be located.
Yeah, TC can be located, any parameter, right? I just say that lambda max will be a function of all parameters of the Hamiltonian, plus additional one which is from the environment. Okay, beta. Okay, so you can take any of the parameters. Right? Take the eigenvalues, vary one of the parameters, and if you see a crossing with respect to that parameter, that will be called the critical value of that parameter. It can be beta, it can be any other parameter. Okay, right? So that's what we talked about. You have a largest this is eigenvalue and this is a crossing. So your largest eigenvalue goes like that, but after that it goes like that. So then basically there is so this is this parameter, if you call A, then you call it, this parameter is AC. Okay, that's the critical value. Okay. And also one more statement which you have said, that if it is one dimensional system, because of what we call Perron-Flovenus theorem, which tells us that firstly the matrix is this transfer matrix is a symmetry, right? I mean, and it is positive. So the theorem tells you that the largest eigenvalue is pretty unique. Okay, it's right. I mean, it's not touched by anything else. Okay, so if you take this analogy too far, for example, let us say that lambda plus and lambda minus, they are e to the power beta, e to the power minus beta, right? I mean, so when beta equal to 0, yeah, so lambda plus minus is e to the power beta, lambda plus minus equal to e to the power beta plus minus e to the power minus beta. So that was the value. So if you plot them, right, I mean, what is the value here? Beta equal to 0. One of them is here, one of them is here, right? I mean, one is 0, one is 2. So it starts from 2 and it beta equal to infinity, it goes to infinity. It starts from 0, it goes to infinity. But at infinity, because this term drop out, they will touch, right? So beta equal to infinity means t equal to 0. So if at all there is a transition, it will be only at t equal to 0, and which we have seen, right? So t equal to 0 cannot be a phase, cannot be called a phase transition, but you have an ordered state there, because there is no way you can transit to the other side. Okay, so there is no phase transition there. So, and that also tells us that in one dimension and short range interaction, you cannot have a phase transition. Okay, so basically, so this formula, which I write now, the way I am formulating it, here it looks very absurd, because what I am assuming that to know dk, you need to know t, right? I mean, this is what you are saying, that you know t. But if you know t, anyway you know a solution of a problem, right? I mean, if it's a one dimensional system, you know transfer matrix. Anyway, whatever you want to calculate, you can calculate, So what is the use of this? Looks like there is no use here, except that it becomes very nice in evaluating the things. Mathematically it becomes very nice. Okay, so whenever, so this one only tells us that it will work, this kind of methodology will work for any Hamiltonian which has a transfer matrix. Okay, if you know a transfer matrix, you can follow this, but you have to know this. So wherever you can write a transfer matrix, you can use this method to calculate different observables. Okay, so for example, we calculated what is the we wanted to calculate one observable. One we already calculated, like this expectation value of plus. Okay, we wanted to now define a correlation function C of r, which you say that, let us say, plus at site I and plus at site I plus r, this expectation value, minus plus square, because wherever it is, it doesn't matter anymore. We know this. Okay, so in terms of the matrices, you know how to write it. Okay, but can you just to refresh, right? After lunch, refresh yourself. Can you tell me what it is? So this one is, the first one can be placed anywhere, right? I mean, this plus means d. So you can put it at the first side, d. So that is basically first one is d, and then this is d. This distance is r. So this is, you can put anything, right? I mean, all you are trying to calculate is the number of configurations which has d at a distance r. Okay, and rest can be anything. Okay, divide by total number of configurations. So d, and with proper weight. Proper weight of a configuration is already taken care by this, by construction of this matrix. So d t to the power r minus 1, and then d, and then t to the power l minus 1 minus r. Okay, so that cancels, right? I mean, this is correct. So so you have to take this divide by, so this will give you all configurations, right? I mean, this divided by trace of t to the power l. Okay, so trace of minus square term, minus, so this square term is just d t to the power l minus 1, and trace of that divided by z, of course, this partition function, and this square. Okay, and then we said that these calculations we will not do for Ising model. Of course you can do, because you know the d's and e's which I have written somewhere, maybe I erased. Okay, you know this d and e, you can put the matrices, and t to the power k generally right? I mean, so you can calculate this. I'm sorry. Okay, so this is what this is the partition function, and this is also the partition function. So this is want to calculate in general, like want to know how the structure look like. Okay. I think I'll use this board at this test because this part is not needed anymore. So now, as I say that the t for t you can write this eigenvalue equation t u equal to u d that I explained, and so basically t can be written as u d u inverse. Okay, u is some matrix that also I mean, we'll do it generally. For Ising model you know this, but for the time being you forget about Ising model. You are just thinking of some Hamiltonian which says each site has certain number of variables, and all you want is that it has some kind of transfer matrix representation. So D and E somehow you know. If you know D and E, then how to calculate it? Okay. Okay. So you D and E, that's the meaning you also know T, right? So you know T equal to U D U inverse. So let us write this one. Okay. So this equal to that. So what will be the next term? So if you put D here, this is T to the power R minus 1 is just U D to the power So this one we have to put some alpha other one. So let us call it capital lambda. Okay. You don't like it? It's eigenvalue lambda. Okay. So I'll use that notation. Okay, right? I mean, so before going there, I mean, this is still I am written it in Ising form. Okay. So let me just, I mean, you know what to do. D, if you have a 1, then 1i, 1r plus 1, right? Then this will be d1. Then that's not a problem. So generally I am doing it. So this is not only plus plus in Ising model. This can be any species in that Hamiltonian, and corresponding matrix is D. Let us say. Okay, that's the word. Is it okay? Is it okay? Fine, right? So this is correlation of one variable at a distance r. In Ising model, I choose that variable incidentally to be plus. In other models, you can choose any of the variables. Whatever the variable, the corresponding matrix, I am taking it D. Okay, all I need is D and T, nothing more. Okay, so basically this equation doesn't need anything else. So D corresponds to whatever species you choose in a given model. Okay, so let us write that. So this is equal to trace of something divided by Z, and this is D. I write that. And T is just T to the power R is just U lambda to the power R minus 1 and U inverse. Okay, and then again D, and again this U T to the U lambda to the power L minus 1 minus R U inverse. Okay, so I take this away. So this is the one. I just take the first term. This term. Other one I am not taking. We'll do it later. Okay. So this is how it will look like, and divided by Z is also there. So Z also let me write it. Divide by trace of T to the power L. Okay. So this is anyway is there. Okay. This is the first term. So now because of this this is symmetric. You can take, if you want, you can take this U inverse also to this side. Okay. So let us take it from here, put it here. Okay. So U inverse du. Okay, I take it here.
You need Q to be finite. The trace of
Q is finite. Q is finite. Q is less than infinity. Okay. So this Q.
You can point this out. Trace AB equal to trace B doesn't work for infinity.
Yeah. So I think I discussed with some of the.
Can you ask them for an example? They would probably.
Yeah, XP this.
There some of them. Those which I discussed, don't tell others. Others should know. So you know that that. So I tell you. Let us say that there is a you have seen this commutation relations. I'll just give you. So let us say AB commutation equal to identity. Is it possible? Right. So what is, if you take trace both sides, what will happen? Trace of a commutation is what? I mean, then you should not. No, okay, so 0, right? I mean, usually this is AB minus BA, trace of AB minus trace of BA. Because of cyclicness, this is 0, this side is 0. But trace of I is just the dimension of the space, right? I mean, the dimension of the matrix, okay? So how is it possible? This equation, you cannot take both side trace. So that means that the equation cannot be valid, okay? You cannot have a representation of A in finite dimension. If this equation is satisfied, then you cannot have it in finite dimension, okay? So for example, if you take A dagger to be with something, some I, okay? That delta I, whatever, that is I, identity matrix. So if that is the case, then if you take both side trace, right, I mean, that will be 0. So A has to be an infinite dimensional matrix, and you know that. Okay, if you want to represent it A, it is infinite dimensional matrix. So trace this formula. These are all true for finite dimension. What will happen in infinite dimension we will discuss. Okay, so this no phase transition is true only when finite dimensional transfer matrices. So I am talking only of finite dimensional transfer matrices, and that actually keeps me Q less than infinity. Okay. Okay, so now just I want to write this. This is the first term. There is the second term, but we'll because there is certain simplicity we still want to see, and if you understand that, we can utilize this in calculating the second one. Okay, so let us try this. So U inverse I take it here, and then what I do is that this one and this one are the same. Okay, and this one, if I have to write t to the power L, this can be also be written as trace of U t to the power L U inverse, that U inverse goes, so this is just lambda to the power L. Okay. Right, I mean, that's what you get. So now you can see, if you call it d tilde, so look at this equation, d t to the power r minus 1 d this, now it is just U inverse du, that is d tilde this. So under the trace, all what is happening is that you are, right, I mean, you have a matrix, right? I know when you start with your transfer matrix, that was in your standard basis, right? I mean, when you write a transfer matrix T equal to e to the power beta, e to the power minus beta, e to the power minus beta, e to the power beta for IG model, this is already written in a standard basis, okay? So when you diagonalize, okay, the same matrix becomes a diagonal matrix with the eigen basis, okay? So so this matrix goes to, so if you take your U to be the eigenvectors of T, okay, then this one in the eigenbasis becomes just lambda. So now you should have a question, what will happen to the other matrices, right? I mean, because it's the same transformation. How do the other matrices will look in the new representation, right? I mean, you have in the eigen representation, not in the standard basis. So D was looking like that in the ordinary representation. But if you go to eigen representation, how does D will look like? Okay, so the general one is that D becomes D tilde. Okay, so D. So if this goes to this in eigen basis, any other matrix A actually goes to U inverse A U. Okay, so when you go change a basis transformation, like standard basis to another basis called whatever basis, eigen basis. So whatever the matrix which gives you this transformation, that will also transform all other operators in the space. Okay, right, when the vectors are transformed, like any vector V goes to U, any vector V in the space will go to U times V. That's the one. If it goes like that, then the operators will go as U inverse AU. Okay, the operators transform like that. Okay, so when you are thinking of writing these kind of things like D1, D, T or whatever you are writing in the standard basis. You could have written in a eigen basis, then it would have been much simpler. So basically here, as if D tilde, in the eigen basis, you are, instead of writing D, you are writing D tilde. Okay, and D tilde is always related to that, and this is just represent the same matrix T, but you are writing lambda. Okay, I mean, no, I calculated it. Don't look at me with a mistrust. I calculated it in front of you. I'm just representing this. How do you do it next time? Do you write U inverse all the time, or do you do it like that? All I'm saying is that when you are looking at these matrices, just think that you are writing it in the eigen representation. So whenever there is a T, just put it a corresponding diagonal matrix. Whenever there is another matrix which is not T, write it corresponding transformed matrix. matrix. Then it will be, that will be same thing. Okay, so that's what I'm doing. So now, okay, and this one remains same because T just transformed to lambda just directly. Okay, so we will use this. Okay, so now if you do this transformation, let us see what will happen. Okay. Okay, so now let us look at this lambda to the power r minus 1. So eigenvalues, this lambda corresponds to eigenvalues. So the lambda is a matrix which is everything lambda 1, lambda 2 like that, and lambda q. No lambda d. You do not know what is the dimension. It may be q, may not be q, whatever the dimension of the space. Okay. Okay. So now I have also taken, and then everything else is 0, and I have also taken lambda 1 strictly greater than lambda 2, greater than equal to lambda 3, and all that. Okay, and this strictness comes from Perron-Flovinus theorem. Okay, the largest one is distinct, that you know. Okay, so now if you put it here, lambda to the power r minus 1, so all of them becomes r minus 1, r minus 1, r minus 1, like that. So this one will be lambda to the power l minus, okay, l minus 1 minus r. Okay, so this will be a matrix like that. Okay, so now let me, instead of r minus 1, let me write it this part. So lambda to the power l. So I just wanted to see what is the matrix look like. So lambda to the power l minus r, lambda to the power l minus 1 minus r. Okay, so this equal to, I can say that lambda max, or lambda 1 is lambda max. So I am also using lambda 1 is equivalent to lambda max. Sometimes I may also use a notation called lambda. I mean, no, right? I mean, so whatever is the largest, I call it lambda or lambda max. So this, just to remember that I'm carrying this index max. Okay, so lambda max to the power l minus 1 minus r. Okay, and then this one becomes 1, and this one, second one, is lambda minus, let us say lambda next max. Okay, so lambda next, lambda 2 or lambda next, whatever the next largest. Okay, divided by lambda x to the power l minus 1 minus r, and similarly other terms. Okay, and all these numbers are even smaller than that because, you know, because of this ordering. Okay, so they might be same, but so if it is possible that lambda 2 and lambda 3 are same, then you have to keep those two terms and rest you drop out because they are pretty small. So this is basically, right, I mean, you know, this is basically, you know, so if you take l goes to infinity, then you can afford to replace all these elements by 0, right? I mean, l goes to infinity because these are much small. Why I am keeping this? This might cancel somewhere else. I will see. If it doesn't cancel, then we have to, we can also drop this. Okay, so I am keeping this for the time being because first order at least I have to keep. Okay, because if something goes to 0, at least you keep the first orders. At the end, if you don't like it, you drop it. Okay, so I am keeping this term. So the rest of them are 0. So now let us rewrite this. Okay, so what is the first one? Right, I mean, this is just I just take this. So this equal to now lambda max to the power l minus 1 minus r, this term is there, and I write these two terms, all other terms are 0, right? I mean, this is just 1 1 and this is 2 2 term, right? I mean, you know, so let me call it for the time being, I call this one is alpha. Okay, so lambda to the power max this, and this matrix is just 1 1 plus alpha 2 2. I mean, you know, this is the eigenvector of, right? I mean, this is 1 1 and this is 2 2. This is in the standard 1 1 and 2 2. Okay, but the same thing cannot be done here because r is something which can be anything, right? I mean, you know, it can be 1. So you cannot do that approximation. Lambda to the power r can be 1. So this will remain like that. So now multiply these matrices, right? I mean, you know, so let us take one term again here. This one will be similar, you know, 1 1. So if you put 1 1 here, so then this will be just 1 1 this side. Okay, so first term, so this equal to this term. Are you with me? Right? I mean, this is the matrix. This matrix is just that. This is that. This is this, and this is represented like that. Okay. Am I losing somebody already? Okay. So now what you do is that take this one. So if you put, so let us say that it is only that. So then if you put it here, here you get this number which will go out. So let us write. So this one, so lambda equal to this. So I mean, this is a separate calculation. Okay. Now I continue with this. Okay, CR. So CR equal to, so from here you get lambda max to the power L minus 1 minus R. Okay, and then, and whatever it is written here, okay, let me write it, trace of U inverse D, okay, let us call it D tilde. I have a D tilde and lambda to the power R minus 1, again D tilde, it's in the Eigen representation. So, and this one is just 1 1 now. Okay, so of course 1 1 plus alpha 2 2. Okay, this is the matrix. This I taken out. So this is under a trace. Okay, so now the first term is just you take 1 1 this side, 1 1 element of that, right? Okay, so I hope I'm doing still fine. Maybe I'll go there. No, there is no way I can go there. Where here? Can I erase this? Okay, I'll use one more thing and then I'll go to the other side of the board. Okay. So what I do here is that this part will be just 1 1 element of that, right? I mean, so the first term, so this equal to lambda max to the power L minus 1 minus R, and this is whatever it is, but this will be just 1 D tilde lambda to the power R minus 1 D tilde 1 plus alpha 2 and D tilde lambda to the power R minus 1 D tilde. Right? I mean, no, so because this 1 1 just becomes element of that in the trace. Okay, so now we just have to find out what exactly is this these numbers. Okay. Okay. In this one you have also when you write CR, trace of this divided by this. So this one is also there, trace of lambda to the power L, and this is also lambda max to the power L. Okay, so divided by lambda max to the power L is anyway there. Okay, so this is divided by lambda max to the power L. Okay. Okay, so now if you have I will take, so let us take in the first term. So there are two terms. So let us take in the one term, only one term. So the first term equal to, so lambda max to the power R minus 1 whole into, okay, 1 D tilde lambda to the power R minus 1 D tilde and 1. This is the term. So let us look at what will happen to this term. Okay. So this term, you can see that. So what is this? What is this term? All right. You know this. Let us write down this matrix. Okay. So this matrix is just lambda max to the power R minus 1, first term. Second term is lambda max, lambda next max, or lambda 2 to the power R minus 1. This is the matrix. Okay. And if you, this is minus R minus 1. So this is lambda max to the power R minus 1. So you can say that this divided by lambda max to the power R minus 1 is, this is just 1. Okay. So this is the matrix and I am taking this part inside. Is it okay with you? So I am putting this part inside. Okay. So I am writing that lambda max divided by 1 divided by lambda max to the power r plus 1. Okay. So what will happen is that this will become a constant cofactor. This is just lambda max. This is lambda max to the power r will cancel. This part will be independent of r. That's the point. Okay. This r cancels out. So this one will be just lambda 2 divided by lambda max to the power r. Okay. And there are other terms, but the dominant term is only that. Of course, there will be lambda 3 by lambda max to the power r. Okay. So those terms are there, but so the primary dependence of r dependence comes only from here. Okay. So other things, there is no r anywhere. This d tilde contains some coefficient, whatever, but there is no r there. Okay. R is only comes here in this matrix, but first one that cancels out. Okay. The dominant one that cancels out. So the next dominant one will remain. Okay. So basically what we'll get, so that alpha is not needed. I mean, you can see that this alpha is not, I was just carrying out, but this alpha, even if this one is not needed, if you just the first term, if you take the first term, that is enough to give you a correction here. The correction in terms of r is just lambda 2 by lambda max, lambda 2 to the power r minus 1 divided by lambda max to the power r plus 1. So if you multiply, right, I mean, if you have these elements, some elements, there are matrices, you multiply, take, this is a scalar, finally eventually you get a scalar. So there is only one term which will come with lambda 2 divided by lambda max to the power that, okay, and there will be other terms, lambda 3 by that. But this is the most dominant because this is the next largest eigenvalue, this is the dominant one for large r. Okay. So in general, your term is, first one is constant, right, I mean, first term is a constant. Okay, first that will be subtracted by this. Okay, first term is a constant here, which I have not shown it. If you do it carefully, it will, right, I mean, we can show that it subtracts there. Okay, so there is a thing to subtract here. Okay, so basically the first term, you can see that first term is a constant, and second term some constant plus some coefficient times lambda 2 divided by lambda max to the power r. Okay, because this minus, there is also minus 1, then lambda 2 by lambda max, something you have, I am putting everything in a coefficient, I am just looking at how the r dependence look like. Okay, so this will be this constant plus something lambda 2 by lambda 1 to the power r. Okay. Okay, so and then it, then it continues. You can call some other coefficient and lambda 3 divided by lambda max to the power r, like that. Okay. So your correlation function. So basically this constant, when r goes to infinity, I mean, physically that this one becomes that. Okay, this, because this r goes to infinity, this just this is just a joint probability, and they become completely independent, and they become just a simple product. So when this becomes product, this one has to cancel out. So it is a good exercise to check, or maybe in some tutorial we will do that this constant is exactly what is written here. If you calculate this one, the constant will exactly come to be what you get here. Okay, so that cancels out. Okay. Right. So because you are subtracting out this one, r goes to infinity, so it goes to 0, and this function, right, I mean, if you say that, so the correlation function now, this constant goes out, so the correlation function will just look like that to the first order, right, I mean, so the correlation function CR is just proportional to lambda 2 divided by lambda max to the power r. Okay, CR goes as that. So now, not only one component, if you do for the other component, it will also come something like that. The coefficient will change, but the correlation function, the general behavior is like that. Okay. Two part anyway, there is a L is there, lambda to the power this r minus 1, there is a L, this alpha was there, but look at what is alpha. Alpha is this divided by L minus 1, this is also 0. I could have dropped it from the beginning itself, I was just keeping, because that is also lambda 2 by lambda max, is might contribute, but it doesn't. Yes. So this is in the final calculation. It's just I kept for safety. I could have started with this is 0 to start with, just only one element. You don't need anything. So you can keep in your calculation. This is once you should see that this one doesn't contribute, because you might ask what happens to lambda 2 by lambda 1 there. So that's the one I kept it here. But L goes to infinity. This also drops. So you can keep only So basically lambda to the power L minus 1 minus r, this equal to just lambda max, that's your formula. Lambda max to the power L minus 1 minus r times 1 1. That's all. Other one is not needed for the calculation to prove that this one is lambda 2 to the power r. Okay. So now lambda 2 is less than lambda max. Okay. So that way this is a decaying function, right? I mean, this is the exponentially decaying function. So if I want to write it's an exponential function, so this equal to, this is proportional to, because I do not know the coefficient. I mean, this is still correct because I write proportional to, but this equal to e to the power log of lambda 2 divided by lambda max. Okay, e to the power this times r. Okay. But do you know what is, whether this is positive or negative? Negative. Okay. So to make sure, right, just to make it prominent, I put it just a mode and put a negative sign just to tell you that it is negative. Okay. So now this usual functions, when you see, this is e to the power minus r by xi. Okay. That's the correlation length of a system. Okay. So what is the correlation length then? So xi inverse equal to log of lambda 2 lambda next max divided by lambda max. Okay, that's the general formula. Okay, or you could xi equal to this inverse. Okay. So now, as I say earlier, that whenever eigenvalue crossing happens, right? Crossing, when does a crossing happen? When the second largest meets the first the largest. Okay. Okay. So when lambda, this one actually approach this one for some reason, then this is just infinity. Okay. So at the critical point, the correlation length goes to infinity. Okay. That's the general result. Okay. So this is what I wanted to say about the correlation function. So this is independent of the model which I studied. So please.
In the end of the previous class, when you were discussing these first order and continuous things, for first order transition, even at the critical point, correlation function can be finite.
Can be finite, yeah.
So how do I do that?
So this is also, good question. Yeah. So that is basically, this goes to 0. Both of, right? Both of them modify somehow, right? Both of them modify.
But the ratio becomes 1. This ratio, right? Because they touch each other.
Yes.
So
Where
how
does
do I get a finite number from this formula for first order?
Well, right, when any of the two eigenvalues in this calculation become close, you should be doing the calculation again. Yes. So then you can, so how they approach. So when you come here, how both of them can go to 0, right? This minus that or whatever, they become same, but the correction could be of the same order. It will not be directly that, because you have to keep the other terms also into account, because when these two, right? Only when did you calculate what I do, right? I keep only one term and left that everywhere. But when actually they meet, I have to keep both the terms and keep another term. Okay, and the calculation has to be done again. So it's not that simple. So you are asking that why for the second order I could still argue, and why not for the first? Yeah, okay, so that is little, yeah, okay.
The derivation from analytic function of z,
Huh.
that is due to you are approximating the z as the maximum value of the maximum of eigenvalue. But say keep the z as say lambda 1 power l plus lambda 2 power l. Then the analyticity won't break, right? Then if you don't do the approximation.
No. So right, so whatever I said, that generally you expect that if you are looking for this lambda max, it will go here and go like that. That is kind of true. The calculation has to be done separately once again, because that is exactly the point, right? Just because there is no analytical continuation at the point where this non-analyticity come about, it's not that the calculation you should do done earlier, you just directly apply there. You have to do it little carefully again to get the corrections well. Yeah.
So probably, so if I just keep keep the next leading order, then you're saying for a first order transition, I can show that the number is finite.
It can be, yeah, in some, yeah.
Partition function is just the sum of exponentials. And exponentials are completely analytic functions.
Yes.
So how can you derivative is discontinuous? It's only in the large limit of L.
Yes.
For large L, only phase transition can be.
Yes. Because for any finite L, there is no phase transition. But that is very simple, right? I mean, you cannot get a phase transition, right? I mean, if you want to get a phase transition, for example, right? You want to look for an order parameter, right? I mean, some order parameter, some side it is 0, some side it is non-zero. If you want to plot such functions, the actual function is just like that, right? I mean, some function which will look like that. No, but don't forget the other part. Draw it like that. This is the function. So this function has a kink. Okay. So there is no way in a finite system to produce such a kink. Unless you push something to infinity, this kind of things will never happen. Somewhere, you have a small parameter, something you have to push to 0. For example, either epsilon goes to 0, L goes to infinity, T goes to infinity, something, all the limits has to be proper. So if you have all the limits which are taken, for example, if you stand exactly at epsilon equal to 0, then the only small parameter remains in your picture is 1 by L, and that has also goes to 0, otherwise you don't see this kink. So I'm just saying that whatever, in a scenario of phase transitions, you have many small parameters, okay? So one parameter is the distance from criticality, I call it epsilon, okay? Maybe in the system there is a field, I call it H. H has to be also 0. In Ising system, there is a small parameter 1 by L, that is also has to be 0. There is a time you have to wait sufficiently long, otherwise you don't get the stationarity. There is also 1 by T, time, that has to go to 0. So anything you want to write correctly, if anything you want to write will be a function of epsilon H 1 by L 1 by T. Okay. So I'm saying that you can keep any of, right, I mean, let us say that this is 0, actually 0. Okay. You can study if this is 0, this is infinity, actually infinity, this is 0, then you see this kind of non-analyticity only when epsilon equal to 0, because everything is 0 is the point what you are looking for. Okay. So if epsilon is already 0, H is 0, T actually you have taken proper, then this is also have to be 0, right? I mean, otherwise you are not at the critical point. So in finite systems there is no critical point, but you are also, right, I mean, I just 1 minute. So your questions, like, for one other question can be asked, that it is only exponential, right? I mean, these functions, correlation functions are exponentials, but this is not something which people who are acquainted with phase transition, they know that it's not only exponentials, no? I mean, you have also power laws, like, actual correlation function in general systems are something like that, divided by r to the power something, like, let us call me, for the time being I call A, d minus 2 plus eta. I don't want to go to there. So some number, it's also power laws. So now question is that how do you get power laws, right? I mean, it's just exponential. So this is a confusion for many people, like, how can you get power laws from exponential?
But if you add many exponentials.
Yes. So this is true. This kind of calculations, I'm saying that this term is there and this term is there. There are other terms are also there. So as long as it is finite, and if these gaps are not, they're appreciable. If it is a finite system, there is a finite spectrum. So you can identify this versus that, right? I mean, so basically there is a gap which this divided by that is clearly visible, and then you can keep one and drop others. But if the matrix becomes infinity for some reason, right? I mean, if the matrix becomes infinity, then except the first one, like usually, except the first one, the rest is a continuous spectrum, right? I mean, mostly. So you cannot drop all of them, okay? So this R which you are writing here becomes, this is exponential, but this is like exponentials added up with proper coefficients, okay? So that can give you, and continuously, it's an integrated function. So it's basically integration, right? I mean, this R, because it is continuous, next one and next one and next one, this will be something like integration and e to the power minus some R by whatever, A, this like, and with some coefficient here, some like, some coefficient S or something. So yeah, this is just a sum. So, but this sum, I mean, I'm just saying that this sum can be thought as an integral, okay? So the integral can, you can interpret the integral as if it's a Laplace transform of something else, like, because if you write a Laplace transform, it is like some coefficient in e to the power something. So a power law function has a Laplace transform. So you are writing that only. Okay, so it is possible if the matrix is infinity, all these arguments will fail. And true phase transitions, like the one which we are talking about, it's not possible in finite systems. Okay.
Just make a small comment, right? I mean, of course, if our system is big enough, I would need a extremely fine resolution of my instrument to distinguish a true transition from a transition, right?
Yeah.
So of course, experimentally, you would still call it a transition.
Yeah, okay. Yeah, okay. So the point is that when there is a phase, this discussion will be coming there, maybe. So in a phase transition, you know that that's the only point which is critical is this point. The non-analyticity is only this point. But who has seen this point? Right? I mean, there is no way. So if you are saying that Ising model or maybe magnetism 122.3 degree Kelvin or something, that is only approximation, right? Either it is below or it is above critical point. Actual critical, what could be, right? There is no way to measure it, right? Any number you measure, it is always little less than or little greater than what you are looking for, right? I mean, so there is no way. So you are never here. Doesn't matter what experiment you do, you never at the critical point. Okay. So now question that how do people see it, right? I mean, experiments, how do people see it? So question that if there is a critical point here, the signature of the criticality will be also visible around the critical point. So you can have a scaling and how they behave close to the critical point, you have a signature. So if you know scaling and if you know, so you know how things behave if there is a critical point there. So for example, so you can calculate them. You know that there is a critical point there. Their signature which will be pretty visible to you. So the power laws, although they're strictly available here, right? I mean, so basically these kind of functions, only when xi equal to infinity, you see the power law. Any finite xi, doesn't matter how large it is, okay? Doesn't matter how large it is, exponential will dominate at the large, for large r, sufficiently large r, exponential will be dominant like anything, right? I mean, any power law you don't see. So only correlation length is infinity here, so the power law should be seen only here. But you can still see for a large extent, as long as r is kind of, appreciably large, okay, or L is large, so that this you can see. So that's the point of the criticality. Okay, so I think the discussion on the general behavior of the correlation function, I stop here. Oh, one more thing is that in these kind of systems which we are looking at, the theorem, right? I mean, the Perron-Frobenius theorem only tells something about the largest eigenvalue. Okay, it doesn't tell anything about what will be the second largest. Okay, so it is possible, it is possible in some systems. It is possible that the eigenvalue can be negative. Okay, so then you will have oscillations, if you have this eigenvalue is negative because this to the power r, you have a odd even like oscillations, like you see in antiferromagnets. Okay, so you can have a odd even oscillations. It is also possible that the eigenvalue become complex. Okay, not in equilibrium like scenario where the transfer matrix is symmetric. But if you go in general scenario, it can be complex, but the complex should come in pairs because the matrix is real. Okay, because the matrix is real, all complex eigenvalues should come in pairs. Okay, so basically you have to keep lambda to the power r, lambda and lambda star divided by lambda max to the power r, and this will give a real function again, but it is oscillating. Okay, damped oscillations. So if so basically what you can have is that if lambda minus is positive, or lambda next max, what do you write? Lambda 2. If lambda 2 is positive, remain positive, then you have this function, and lambda 2. So the behavior of the function is that it is just goes like that, is exponential, and if lambda 2 is negative, then you have you have an oscillation like that, these points only, this, that, this, like that. And if lambda 2 is complex, I mean this negative is generally complex, then you have a curve which can go like that. Okay, so you can have all this behavior of correlation functions in general. Okay, so
for example, in the liquid, that's how it would look like.
Yes, generally in liquids, the correlation function behaves like that. So we have what is summing? So we have some works which actually instead of liquids, if you take simply rods of a definite length, Let us say that you have rods in one dimension instead of particles. Okay, just they're diffusing in one dimension, but they're rods. So you can still see behavior like that, because that's the intrinsic length scale, like a liquid. Liquid has a short length scale, right? I mean, into some, right? If you put your hand, it will realize to some extent some perturbations. So that's the way the liquids are. Anyway, I think regarding the correlation function and correlation length, I will stop here. Did I miss anything? I just have a list what I was. Genetic correlation function and decaying function, I think I'm done. So I don't want to say anything else about the correlation functions, and probably the method. Yeah, okay, at this stage I think I would ask some questions, if there is. R to the power a कहाँ से आया? Okay, I think this is something which I always want to say. Arnav will talk more about criticality, but let me introduce a little bit. So if I have a system, if I give you a glass of water, let us say -3 degree, glass of water at -1 degree, glass of water, my glasses are like that, +1.
Why is the glass changing with temperature?
Plus the same glass, okay, +2, okay, +3, okay, the temperature difference in 2 degree. Okay. So now I just say that I have this, and I just wanted to tell you that take 2 glasses and tell me which one is these 2. Ask you which one is -1, which one is -3. Will not be able to tell, right?
You give me a thermometer.
No, just look at it and tell me. I mean, you cannot. I'm just saying that if you give you these 2, you also cannot tell me which one is what. But if I give you these 2, you will be able to tell me. So question that do you know why? You know there is a phase transition in between 0 degree. So now tell me why. So question is that why you cannot answer me it more clearly. Why you could not see a difference there?
At least for small variations of the current.
Sometimes now just -1 and -3. That's specific. Why don't you see a difference there? Is it not that the glass of water at no, okay, let us talk these 2, it is easier. So why don't you see a difference there? Is it not that there is a difference? What is the difference? Which one? 2 degrees?
Yeah, that's the difference.
No, no, but intrinsically, that I told you, right? Now, what is the difference, right? Of course, when I'm saying that it is 2 degree, there must be some way somebody should be noticing it, right? At least a thermometer can notice, right? You cannot. So, what is the difference, actual difference? What is the difference in the liquid, which is in water, which is +1 and which is +3? What is the difference? Internal energy. Anything else in terms of scales? Which distance? Mean field? So what about the right? Okay, some vibrations, right? Where the water molecules are probably colliding little, right? Maybe the length scale which is involved there in the collision is much larger here. Okay, and how large compared to 1 and 3? Just give me a number, something. Some nanometers probably, right? Probably some order. Okay, so I'm just saying that exact number I do not know, but it is some number which is not perceivable in human scale. Okay, and that's the reason you don't see it. How to see it? How to see it is that you create something which see it, right? You take some other thing like you don't know, actually you do not know what is temperature and how to do it. So you take something else like mercury, for example. What you do is that these vibrations, right? It will feel the vibration better and it will swell better. With a little bit of change in vibration, even in the nanoscale, it will just swell. And then even that is not enough. You have to put a capillary to see even the little change. And that's the way instruments are. Okay, all instruments, by the way, eventually does this job. Something which is not visible or not perceivable to human, right? It will bring you to that scale, right? Doesn't matter whether the galaxies are there. You want to see it on a A4 size paper. That's the way it is, right? That's the way you want the instruments. Okay, so there is a difference, and the size of the instrument is also as much as you want to reduce, like moon, this much of telescope and galaxy is that big. So anyway, and the same thing is true from the other side also. Quarks 26 kilometers, that's what you need. So anyway, so I'm just saying that there is a difference between +1 and +3, but you don't see the difference because things are happening in some nano or micro scales, like which is not perceivable. But when you go from here to here, the changes actually occur, right? I mean, seriously, there is a change occurs which is in your perceivable scale, and the change is not that if you put a glass of water in a refrigerator it will freeze, bottle will freeze and do whatever, a lake will freeze and the ocean will also freeze, right? I mean, it is independent of the system size, okay? So the phenomena which was occurring in nanoscale is now occurring in kilometers also, okay? So you want, right? I mean, if you are passing such behavior from here to here, then you want something which is scale invariant, right? The one which is visible in all scales, okay? And you do you know? Yes, yes. So do you know a function which is invariant in all scales? Power law. Simple is x, for example. Just you zoom up, doesn't matter how much, it will look like that. Like the fractals also you see. There are power laws. So for your exercise you just take print -1 to 1 x square. Print it in a A4 size paper. Another one -1000 to 1000 x square. Another paper, okay? Hold it together, okay? You don't find a difference, really. Right, I mean just x square. So anytime -0.001 to +0.001. Plot it, print it and show it. There is no difference. They are on the top of each other, okay? So every bit, right, I mean every small bit if you zoom, it is there. So not only zooming in, zooming out also it is there. So whenever you are passing, so phase transition, by definition you mean that there must be macroscopic change, right? I mean that's all you want by phase transition. So it's not that here, this was not a phase transition, this is only a temperature change. The state of the system changes, right? I mean it's still a liquid, but it's a liquid at 1 degree and liquid at 3 degree. But there is no, so basically that doesn't happen. That is the only place, right? I mean if you pass that, that's the place where you need a scale invariant function. So now if there is a scale, the function should be behaving like e to the power minus r by xi. Okay, that's the xi is the length scale, that is this nanometer, whatever. So this side also you have a scale, right? Something, but this one is a power law, right? But then how is it possible that you connect this side there is a scale and then exponential and then you say now power law and then you say exponential and exponential. Some way you have to make a continuous continuity of the variables, and the function like that f of r, this does that. Okay, so if you say that xi is some finite, any finite number, this will be dominated by that. It will look like exponential because exponential is the most dominating function. So in the both sides it is just exponential. At here this xi is infinity. Okay, so then you get r to the power a. Okay. By the way, I apologize, I give you a wrong example, but that's the only example of phase transition you know in nature and you see in nature. But this phase transition is a first order transition, like liquid one. So this is not a proper example, I just wanted to give you a feeling of that. But this is exactly what happens when you magnet, when iron becomes a magnet, okay? This is exactly the same phenomena happens. This here, we have little involved, we'll not discuss now, okay? You got your answer to the question, like, why power law? So it is inherent, right? I mean, you have to have. It's by demand. If you are having a phase transition, you are having that.
Does it relate to unfresh criteria for phase transition? Unfresh criteria something.
Is there? I am not remembering it well now. You remember it? Unfresh criteria.
That just tells you of the order of the phase.
Okay, yeah, that is the order of, but it is with the order of phase transition that I talked about, right? I mean, how it cross depends on, it depends on how.
Like specifically mentioned, the derivatives should diverge. So cusps are not.
No, but which order? I mean, it also
First order, second order. Yeah.
If nth order of derivative of this is, I don't know which criteria unfresh, yeah. So nth derivative of the partition function diverges, this is called nth order phase transition.
But I think, at least our modern understanding is, of course,
Non-analyticity.
Order parameter, and if the order parameter changes discontinuously, that's a discontinuous transition, and if it changes continuously to 0, that's a continuous transition.
Yes, yes.
And there are only two.
Yes.
That's the way to look at it.
Yes.
That's the modern
Now,
Yeah.
it's only first order.
But then there is
Even better is discontinuous and continuous.
discontinuous. Yes, yes. That is.
You always remember. There's no way to forget.
Yeah.
I'll discuss some of it in one of the tutorials.
Yeah, but I just kind of don't want to confuse this for the class. It is fine, but I'm just saying that recently people find something which is neither this nor that, some kind of things. So we'll not discuss like.
You mean there is an order parameter there? Because if there's an order parameter, it can only be one of the two.
But if it is so, right, it's the other one. Even if the order parameter is discontinuous, do you see power laws or not power laws? Sometimes it is possible to see power laws even if it is some cases.
There are exceptions.
Exception, yeah. Not I'm saying. So this is not relevant to the class. Okay. So I'll change gear now, and next class. Okay. Okay. Before I go to another question here, I'll discuss another question in equilibrium, and then from tomorrow I'll do non-equilibrium. Okay. Any questions? Any further questions? I'd be happy to answer now.
One question.
Yes.
I mean,
This one was not clear. Yeah. Okay.
Of course, you said that. If you have longer range systems, then it becomes harder to do this method of transfer matrices. But this is just a vague question. I mean, have people tried to explore like increasing the range of the interactions? Can you somehow, in some manner, show that there must be a limit which gives you a phase transition?
No. Okay. So now, okay. No. Let me answer this question. Right. So point is that you have Ising model, and this was interacting with only that. Okay. And this was interacting with only that. So and that could not show. And for that the transfer matrix is 2 by 2. No, sorry. This is white 2 by 2. And you saw that finite dimension, no phase transition. So now question is that instead you take this also interacts with next nearest neighbor. Okay. So you can also write a transfer matrix for this one, this case, both of them are there. You can write a 4 by 4 transfer matrix, and similarly, doesn't matter what is the range of interaction, it will not have. So now question is that short range and long range, what is the difference between short range and, so if you interact with 50 lattice sites, this one, that one, up to 50, is it short range, it is long range, okay? Well, so because in your criteria, you have a system which is L going to infinity, anything which is finite has a right, this divide by, because divide by L is 0. So doesn't matter. So if you cut it off, this is not a power law. So you don't see a phase transition. Okay, clear. So now short range and long range come. So basically, if it is exponential, e to the power minus r, it interacts with everything, but very low intensity, right? R goes very large. So this is also short range, like, right? Because effectively up to xi, right? If it is e to the power minus r by xi, then of the order, if the number of sites which you want to interact, that is of the order xi, you have relevant interactions like appreciable value for the interaction. Beyond that you can drop, like those are not very appreciable numbers. So that is also short range. Although the particle interact with everybody, it is still short range. So now the demand is 1 by r to the power alpha. Okay, so this is a long range interaction generally, right? So if you take Ising model, for example, let me say what I mean here. So that is basically Hamiltonian H equal to S of I plus R. Okay, any R, and then there is a J which is J0 divided by R to the power alpha, summation over I. So basically each spin interact I and J, no I and R, all R. Because each I interact with all other spins, doesn't matter what is that distance, everything interact with everything, but then the strength depends on the distance between these spins. Okay, so in these situations we will have a phase transition. Okay, so the demand, just I quote the results. So alpha less than 2, you have a phase transitions. Okay, alpha greater than 2, you don't have a phase transition. This is only 1D systems. Okay, and alpha equal to 2, there is a very nice paper. So this is, you may have a first order transitions. If you have, you only have first order transition. Okay, so that's the situation. So basically alpha greater than 2, which means the interaction decays very fast. Greater than 2 means 3, 1 by r cube. So if it is, this 2 is always a very sacred number. I'll discuss some other day why. But this is, if it is 2, right? If it is faster than 1 by r square, anything which decays faster than 1 by r square is like a short range, Although the actual it is long range interaction, but there is no transition. So this is behaving like this one or like simple Ising model. Okay, so that's the general results in Ising systems. Okay. So if it interact with 50 or 100 or 1000, it doesn't matter. All of them are short ranged because A is anyway infinity. Okay. One other thing which I wanted to point out in this context is that in this situation you start with a you have an Ising model. I never talked about dynamics, right? I mean, you have an Ising model, that there is a Hamiltonian. Then I said that partition function. When I write partition function, I am only talking of the stationary state, right? So in an actual system, like there is some Hamiltonian. You start with some configuration or something. It will evolve with time. So the time evolution is not given. So why? Why, I mean, of course I did not take it. You can say that my wish. No, but here you did not need. Because the partition function depends only on the probability of a configuration in stationary state, okay? And that one is already given. Irrespective of what Hamiltonian, it is already given. So I don't need to take a system, evolve it to the stationary state and need to know what is the stationary state. I don't have to calculate that. It's given. Somebody gave it, Boltzmann, okay? So I don't have to calculate it, okay? I'm trusting, I trust that result, I'm writing that and then proceeding further. So question that actually, if I have to do this is, maybe a simulation or something, how do I do it? What exactly is that Ising dynamics, okay? Okay, so that is needed because here you have a Hamiltonian. As I say, when you go to non-equilibrium, I don't know whether it can be described by a Hamiltonian, okay? Because I don't know. All I would know is the dynamics. It's only the dynamics of the system. Because given a Hamiltonian, all you write is the equation of motion which tells you how the system evolves. In non-equilibrium, I will tell you how the system evolves directly. And from that I have to derive what exactly is the stationary state, okay? So it is good to know what is the dynamics of the system, okay? Because the dynamics of the system would have some relation with the D's and E's which I am talking about. Because how the system evolves tell you what is the stationary state. The stationary state will give you some D and E. So I don't need a Hamiltonian somewhere, right? So the dynamics should be somehow related to this D and E which I am talking about. So let me tell you what exactly is the dynamics, how, right? So one should be very clear, right? When you talk of harmonic oscillator, classical harmonic oscillator, pendulum, okay, H equal to P square plus Q square, right? That's the, and then you know how to write the equation, motion x double dot equal to minus kx, you can calculate that, okay, next step. But point is that if I ask you, write the equation of motion of a harmonic oscillator in 20 degrees centigrade, right? How does it evolve? Can you write the equation of motion of a harmonic oscillator at 20 degree centigrade, right? Right? Temperature is not a concept which is there already in this particular picture, right? It's not there. But I'm just saying that is again, he will write a Langevin-like equation. He's just saying because he will assume that a temperature is some degrees of freedom and there is some random force and this is some kind of assumption. But there is no way. This is kind of it works. Of course, it's a modeling of the bath, like what gives you a temperature bath. That's modeling, Langevin modeling, right? That's a model which works very nice, fantastic. But I'm just saying that this is not the same way that given a Hamiltonian you derive it, right? This guess works pretty nice. Okay, there is no way to write it. So I'm just saying that similarly for Ising model also, right? If I write a Hamiltonian and I want to evolve it at a given temperature, there is no evolution equation for any Hamiltonian. Doesn't matter, right?
I think the reason is straightforward in some sense, right? Because there are so many external things.
Yeah. So basically, temperature. If there is a temperature, external, if you are losing energy, there are other degrees of freedom you cannot take care, and there are infinitely many. So it's a give up situation. So you don't do anything. No, I'm just saying that you do something. No, I'm just saying that there are things to do. No, that's what we see that what to do, right?
You cannot write a completely faithful microscopic description.
That you can write that you can write. So basically, then that gives us also freedom to make choices, right? Langevin is one choice. I will make another choice and I will tell you how Ising model could be evolving, right? Whether actually, if you ask me whether Ising model, if you take a magnet, whether it is evolving like that, I don't know. So, right? I mean, that kind of dynamics, we call it Monte Carlo, okay? And if you do it many times, many of you would feel like probably that's the evolution of the system. I do not know. This is the modeling of the evolution at a given temperature, okay? I tell you how that evolution comes about. Okay, so you have a Hamiltonian, right? I mean, it can be anything. For this case, for the example case, I am just taking summation over I, Si plus 1. Let us see. Okay. So I know that if the stationary state is in equilibrium, then I know that it satisfies detailed balance, right? I mean, now, okay. So you have a system whose size is L, okay? And then there are 2 to the power L configurations. And what are the configurations? So the configurations are listed like that. So like minus, 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 plus, last one is plus, minus, last one is plus, minus, 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 plus, then plus, minus, and then plus, plus, like that. So you list all configurations. So there in number 2 to the power L. Okay. So when you start, right, evolution, the system is in one of the configuration. I don't know which one. Maybe it's somewhere here. Okay. You start some configuration here. Maybe here, this one. Okay. So then you have to evolve. How you evolve the system? Like you right. I mean, what is the point? Is that you remember that 7 SOP problem which I talked about at the beginning, 8 SOP problem. Okay. So there you just move from one configuration to the other configuration. So you can jump from any of the configuration to the other configuration. Okay. So you can jump. So now question that whether should you jump, how to jump, and things like that. Okay. So then I know if the system reaches stationary state, then if you have a configuration C in the stationary state, if you have a configuration, current configuration is C, let us say that the configuration you are going to jump is called C trial, because you have not jumped yet, you are now deciding whether you want to jump, okay? That's called C trial. So probability of C going to CT, and there must be a rate for that, okay? So I'm just saying that WC goes to CT, so this equal to probability of that as if you are in that configuration and you're coming back, PCT WCT going to C. Okay. So this is general configuration and T is the trial configuration. Okay. So this equation must be satisfied. Okay. If you are in the stationary, if you are in the stationary state and in equilibrium state, then this equation must be satisfied. So I will still use the Boltzmann part. So this part is e to the power minus beta EC. Okay. And so basically this one is e to the power minus beta ECT prime. So what I can write that WC to CT, this trial configuration, divided by WCT to C, this equal to P of CT divided by that. So this is e to the power minus beta E of CT minus E of C. Okay. That's the equation, right? I mean, this equation must be satisfied because all I want is that PC is e to the power minus beta EC. That's the equation must be satisfied. So this, right? I mean, if I know all of them, then I know this, right? I mean, but I have still 2 variables and 1 equation. This is the only constraint. So this is not determined uniquely. You can choose whatever you like. Okay. After this, you can choose whatever you like. So you can choose a convention, right? I mean, after this, you can choose a convention, which I tell you, I mean, consistent convention. So basically, what you can say that your trial configuration, right? So let us say that what is the possibility? Your trial configuration, energy of the trial configurations can be larger or smaller or same, right? I mean, so let us say E of CT, E of CT is larger than E of C. Okay. Okay. First, let us call smaller than the trial configuration which you are going that has smaller energy than where you are. Okay. So in that case, so CT to C, I just make a convention. If the trial configuration is lower energy, then I put this one is 1. Okay. So if the trial, right, I mean, these two things has to be fixed. These are the rates has to be fixed somehow. Okay. And you can choose what, as I said, that whatever you want to choose, you can choose. Okay. I'm making a convention that if CT is less than EC, like the one which you are going now, if that has a lower energy, you surely go. Right. I mean, that's the probability, or that's the rate. So what you put is that this one, you put it 1.
You mean the top one?
Top one you make it 1.
Want to go to C.
CT, C to CT, yeah. CT is a lower energy configuration. WC to CT you can make 1. Okay, if this is the case. So if this is 1, then W. So if you take this, then this rate WC2 to C. Okay. So this equal to e to the power beta and e of CT minus C delta E, right? I mean, so this is beta CT minus E of C. Did I make a mistake somewhere? So minus, there is a minus.
So this is okay. CT has the lower energy, so it's some number smaller than 1 as it should be.
Or else you check that inequality.
No, it's okay. See, this is a number smaller than 1.
Yeah, so I put a minus and this one. Okay. EC minus CCT. Okay. So this is just delta E. Okay. So this is still smaller. Okay. So this is smaller than 1. Okay. So basically now CT to C is a transition for higher rate, right? Higher energy, right? Lower rate, higher energy. Okay. So is it clear? So when you say CT is less than this, so then you are C to CT, this trial configuration, this one, you are going, right? I mean, if this is going to lower energy, then reverse is going to higher energy, right? I mean, so higher energy transitions are slower, right? I mean, because it's e to the power minus beta. Other one is 1 and it is e to the power minus beta. At most it can be 1. Okay. So that's your rule. Okay. So for your homework, I'm just saying that take the other convention the same way. If CT is less than that, the same thing is true, right? I mean, so it's whichever way. And then if it is equal, you decide whether to go or not to go independently, randomly and independently, means half probability. Okay. So that can become a dynamics. Okay. Did I? Okay.
So in that case, everything will go to the
Stationary state, equilibrium state. It
No fixed equilibrium state. What do you mean? Fixed equilibrium.
no. If you have a Hamiltonian, you know where to approach, right? You know that doesn't matter what I do, my dynamics is approved if eventually at the end I get a state which satisfies detailed balance with respect to e to the power minus beta h, Boltzmann weight, okay? With respect to that. If it satisfies that, then I am happy, okay? So what I am doing instead, which is, I mean, I'll say a little more about it. Yeah. So which is actually unreasonable. All you want is that at the end it should satisfy. All I am doing it now is that in the step when I am going, in the intermediate step, when the system is evolving, I want to use the same equation. So if it is over assuring, right? If I am assuring that something is true, right? I mean, I only want to check that at the end it should be true. But if you are ensuring on the way that it is true all the time, whenever I am doing it, then of course it will be true there. So that's the way I am doing. So even if the system is evolving, I am using this Monte Carlo, this step, like detailed balance, to calculate, just to get the rate. Okay.
So during that path, probability of going from higher to lower is 1. From lower to higher is not 0. It is there again.
Yeah, it's there because you see. So if you think of a energy landscape, somebody was. So if you just make going to higher energy is 0, don't go because you want to minimize energy. You just, if you lower it, go. So then what will happen? Wait a minute. So what will happen is that it will go from here. It will go here because it's lower. It will take a step here, but it will not go. It will take a step, not go. It will go here. It will not come back because higher. It will go here and it will settle here. And after that, any step it wants to take, it will just be higher. So it will stuck here. But actual minimum is somewhere here. It will never reach there. Okay. So it will, directly, it will stall in a local minima. So that is not a good. So you actually allow this e to the power minus beta delta e. The delta e is the same delta e. So that's the ability of the thing to move. So if you write, if the height is this, whatever, in n times delta e, the probability is just multiplied. This because
that's a very physical effect. It's like an
activation. This is just activation, Kramer's activation kind of process. Because if it is in units of delta e, whatever it is, you jump that. That's the probability directly. Okay. So that is all consistent, and this is one. So what is the rule? The rule is now, if the energy of the trial configuration is lower, you surely go. If it is higher, then you go with a probability p, which is e to the power minus beta delta e, the change in this. So basically these two things can be written as minimum, the probability p, so is just minimum of 1 and e to the power minus beta delta e. Delta e is the change in the energy. Okay. So if delta e is smaller, that means you are going to a lower energy configuration, then this one is larger and minimum of this will give you 1. And this is just two statements in taking in one line. Okay. So now only, can I take 2 more minutes? Oh, okay. No, little more. Just give me, okay. Let us start. So now let us say that what will be let us think of a actual trial configuration. How do you make a trial? So you start with a configuration. You want to jump to a new configuration by flipping 700 spins. Is it allowed? Is it not? You see, if you change at a time 700 spins, what will happen is that you jump a big step. Your energy is very big. So, it's like going from here to here, and then from here to same, let us say maybe here, like that. So you might never find it even where is the minimum. You're jumping, right? So basically it is good if you flip only one spin. That is enough to change the configuration. Okay, that is assuring. So what your trial configuration is, that trial configuration is also a choice, how you choose a trial configuration. So wherever you are, randomly flip one of the spins. That's your new trial configuration. And now see what is the energy has changed and decide whether you want to go there or don't want to go there. If it is a lower energy, you go. If it is a higher energy, you go with probability p, which is e to the power minus beta e. Okay. So you go with that probability once a while you go. Okay. So that way if you move, eventually you reach a stationary state. Okay. So that's the way you reach the stationary state. So now you can see that this Monte Carlo, of course it works, but this intermediate state, if you are using detail balance in the intermediate step, it is unnecessarily slowing down the system, because each step you are ensuring that this is satisfied. Okay. This is not required. So there could be a better dynamics to reach equilibrium state. Okay. If I will not have an opportunity, but I can try to give an example where a non-equilibrium way of reaching a equilibrium state. Okay. Right. So there are so that's
the short answer is you don't need to satisfy
detail balance on the intermediate step. As long as it's the last step, it's satisfied, is fine. But can you develop a general dynamics, right? Like Monte Carlo, at least for a class of systems. Okay. So there are available.
But even this is interesting.
Yeah, this is interesting. No, I'm not saying that this is not bad. This is very good. I mean, it is the only thing we use all over. I mean, all the places. Okay.
I mean, in the sense of teaching a class.
Okay. Yeah. No, okay. So that's okay. Okay. So this is the dynamics. Okay. So now let us drop the idea of energy. Okay. Let us say the Hamiltonian is not given. Okay. Somehow somebody tells you, because if you are jumping from here to here, not allowed, right? I mean, here to here one spin flip allowed. Here to here one spin flip allowed. Here to here, in your dynamics this is 0. This you put a rate 0. So right from here to here, it's a high change in energy. So that is not allowed. It's not one. So you can, in your configuration space, so there are 2 to the power L dots, like these are your configuration. So here to here, if this is connected by one spin flip, okay, then you keep it. Otherwise you just, stick it. So that is your rule on a paper. Okay. P is some fixed number. Okay. So whatever number. So if you do that, right, then you know that you are reaching a stationary state which automatically satisfies detail balance, right? The Hamiltonian is gone somewhere. I mean, it is not there actually explicitly in the picture. So the dynamics, if I tell you the dynamics, you know that it will reach a stationary state, and the stationary state can be described by these D, E, T matrices, which I wrote. Okay? So can I connect it? Okay? Can I connect it? I will only tell the dynamics. I don't know the Hamiltonian. Even the dynamics doesn't have a delta E. I'm not calculating delta E. Put that. Somebody intrinsically calculated for all rates. Somebody writes on a paper. This to this rate. This to that, this rate. If somebody tells you that, you will have no idea. It's a huge paper to look at, table where what to go. But you still have the same problem. Okay? You reach the same stationary state. You don't need a Hamiltonian anymore. So question that given the dynamics, is it possible to reach a stationary state in that situation, and can you write in terms of D and E? Okay? So that's what I will do in the next class. It works on the stationary state only. Yeah. So, okay. So the dynamics.
So here, just maybe. I mean, of course, you can start with two completely different initial conditions and run this dynamics. Both these conditions will still give you the same
stationary state. It is irrespective of initial conditions. Yeah. And this dynamics is stochastic, right? There is a probability involved. Okay. So this is a stochastic process. Yes, the probability depends on the temperature. Temperature, you have to say a priori. What is the temperature? Okay. Yeah.
Of course.
If there is a criticality, of course, this dynamics will help you finding one.
I mean, in fact, this has a very well-known name. This is called the Metropolis algorithm.
The whole thing is called Monte Carlo simulations.
No, but
this particular algorithm, yes. This
is called Metropolis algorithm, and I mean, for most problems where you cannot find the solution analytically, this is one of the ways to.
Yeah. This is Metropolis. Metropolis algorithm. Okay, Metropolis algorithm is just this one, that if it is low you go, if it is high go with some probability smaller than 1. That's Metropolis, and the whole thing is Monte Carlo. Okay, anyway, any other questions? So tomorrow we start with we start with this picture, that some configuration space, some dynamics, and now question that starting from there, can you develop a theory so that we reach a stationary state? It may, the Boltzmann is out of picture now, and we try doing something. Can you find a stationary state and things like that? Okay.